BxMO 2020 Benelux problem number 1. This Olympiad is for Belgium, Luxembourg, and Netherlands. So let's check the problem. The problem is the following. Problem number 1. Find all positive integers d with the following property. There exists a polynomial p of degree d with integer coefficients such that the absolute value of p of m equals 1 for at least d plus 1 different integers m. Again, at first we want to consider some a small example of d. I said before in the previous problems that considering a small example is important, and also there is one idea that is really important in polynomials with integer coefficients, that, let me write that, a minus b divides p of a minus p of b. Look, considering small examples is really general in all number theory, algebraic problems, geometric problems sometimes, and combinatorics problems is really useful. But in each topic, for example, algebra, we have 3 topics. One of them is polynomial, and in polynomial with integer coefficients, the most important idea is this, and it's really useful in IMO and also National Olympiad. So, at first, let's consider a small example. If we consider D1, we need 2 answers for P of M, absolute value of P of M equals 1. If we consider P of X equals X, P of 1 is 1, P of minus 1 is minus 1. We found 2 different integers. So for D1, we found a good example. So D1 is one answer. Now let's check D2. We want to say, for example, degree is 2, x minus a times x minus a1 times x minus a2 plus 1. If we consider a1 and a2 are different integers, then p of a1 equals p of a2 equals 1. And so we want another numbers that p of that is minus 1, for example. So if I want to, for example, replace x with 2, if I write 2 times something plus 1 equals minus 1. So 2 times minus 1. If I consider x minus 3, like this, 2 minus 1. So it plus 1, it would be minus 1. So let's check. P of 2 is 2 times minus 1 plus 1 minus 1. So if I consider this polynomial, P of 0 equals P of 3, A1 and A2, 0 and 3 equals 1, and P of 2 is minus 1. You can find many other examples like this. And also we found a polynomial for d equals 2. Now we've checked some small examples, and now we can move to general d to find some conditions in general d. For general d, degree of p of x equals d, and we know that x1 to xd plus 1 are different integers, and absolute value of them equals 1. Without loss of generality, we can consider that x1 is less than x2, 2 less than xd plus 1, and xi, all of them are integers, different integers. So at first, let's consider special cases. Can all of them equals 1? If p of x1 to the last one equals 1, if we define q of x, p of x minus 1, q of x has d plus 1 different roots, and it has degree d. So by fundamental theorem of algebra, we know that it has at most d real roots. So here we have more than that, so it's equals 0. So p of x equals 1, and degree would equals 0, and that's a contradiction. So some of them must be 1. And similarly, we can use this proof for when all of them equals minus 1, then you define q of x equals p of x plus 1. And so we can conclude that we have both plus 1 and minus 1. So suppose that p of x1 to p of xk equals plus 1, p of y1 to p of yl equals minus 1, and they are all d plus 1 different integers. So k plus l equals d plus 1. Now let's consider x1 with y1 to yl, x1 minus y1. Now we want to use the most important idea in polynomials. What was that? With integer coefficients, x1 minus y1 divides p of x1 minus p of y1, which equals plus 1 minus minus 1 equals 2. Similarly, we can say x1 minus y2 divides 2 to yl divides 2. So x1 minus yj equals plus or minus 1 plus or minus 2. And we know that y1 to yl are distinct different integers. So we have at most 4. It means that L is at most 4 because plus minus 1 plus minus 2, we have 4 different numbers, and x1 is equal in all of the equalities. So L is at most 4. Similarly, we can prove K is at most 4 because we have at least one here from the previous page. So L is at most 4, K is at most 4, and D plus 1 is L plus K is at most 8, so D is at most 7. So we proved that for D greater than 7, the problem is not true. We can't find any polynomial. So we need to consider D from 1 to 7. We've also found for D1 and D2. So let's check some other cases. We want to consider the case that, for example, L equals 4, exactly 4. Let's check that. Without loss of generality, we can consider that x1 equals 0. Means p of 0 equals 1. x1 was this. Because we can replace p of x with p of x minus x1. So we can conclude that p of 0 equals 1. Now, p of 0 equals 1, x1, and we know that if, for example, L equals 4, without loss of generality, we can consider y1 minus x1 minus 2 minus 1 plus 1 plus 2. So y1 equals minus 2, y2 equals minus 1, y3 equals 1, and y4 equals 2. So this is x1. Now if k is greater than 1, we want to consider x2. If, for example, we consider x2 here, there are different numbers. If we consider x2 here, so the difference between x2 and y2 is 3, and 3 doesn't divide 2. Like this, the things that we write. Any difference of xi and y, for example, j, must divide 2. So if here we know this is y2, if x2 is this, so their difference is what? Is 4. The difference is 4 and it doesn't divide 2. And also you can't select x2 4. Again, the difference is not multiple of y1. It must divide 2, and if you say x2, for example, is 3, then 3 minus, for example, 2, like this, equals 5. 5 doesn't divide 2. And also you can prove for other things. So here we've concluded that when L equals 4, K equals 1, and D plus 1 then equals K plus L equals 1 plus 4 equals 5, then D equals 4. If we want to find an example for D equals 4, we can use these things that we've reached. X plus 2, x plus 1, x minus 1, x minus 2 minus 1. So for minus 2 minus 1 plus 1 and plus 2, it equals minus 1. And if you replace x with 0, it would be 2 times 1 times minus 1 times minus 2 equals 4 here. Yes? So p of 0 can't be. So we need to check these things. So let me erase that. If we replace x with 0, it won't be minus 1. Now here let's check what can we conclude. We know that p of 1, we know that p of minus 2, minus 1, 1 and 2, all of them are equals minus 1. So if you consider p of x plus 1, it has 4 roots, all these 4 roots, and you can say, okay, a times this and minus 1. So now we want to select a such that p of 0 equals, we said without loss of generality, we can consider that p of 0 is 1. So if you replace, it would be 4a minus 1. You want to say that it equals 1. So if you consider that it would be 4a equals 2 and a equals 1 half, and if you replace 1 half here, a with 1 half, then the coefficients are not integers. So we've concluded that for d equals 4 we don't have any answer. Now from here we can conclude that k is at most 3, because we've reached contradiction for when one of them is 4. So here we can conclude k is less than or equal 3 and l is less than or equal 3. And d plus 1 equals k plus l is less than or equal 6, so d is less than or equal 5. We've checked for d1, we found an answer in the first page. For d2 also we found answer. We reached contradiction for when d equals 4, so 1 was true, 2 was true, and here we said that we need to check for 1 to 5, and 4 was bad, so the only d that we need to check is 3 and 5. So let's check 3 and 5. When d equals 3, we can say, look like this page, we try to find from 1 to minus 1 minus 2. We say, okay, x plus 1 times x minus 1, x minus 2 times minus 1. P of minus 1 equals P of 1 equals P of 2 equals minus 1. And P of 0 equals 1. So for d3, we found a polynomial. And now let's consider when d equals 5. So we know that k and l are less than or equal 3. K plus l is d plus 1, which is 6. So k must be 3 and l must be 3. Like the previous pages that we said, without loss of generality, we can conclude x1 is 0, means p of 0 is plus 1. Now let's check. P of 0 is plus 1 and we have 3 negative numbers. So 2 of them is from, we can only choose because we said that x1, for example, minus y2 divides 2, x1 minus y3 divides 2. So if we have 3, we have at 1 and 2, both of 1 and 2, or minus 1 and minus 2, both of them. Without loss of generality, we can consider that we have 1 and 2, both of them, and we divide the problem into 2 cases. y3 is minus 1 or y3 is minus 2. So let's check. x1 is here. Now let's check x2. If we check 3, then look, 3 minus minus 1 is 4, doesn't divide 2. If we select 4, all of them are like this. If we select minus 2, minus 2, minus 2 would be minus 4 and doesn't divide 2. So we don't have any choice for x2. And now let's consider case 2. Again, here it's 0, minus 2, minus 1, 1, 2. Now, if for example x2 is 3, then 3 minus minus 2 is 5 and doesn't divide 2. And also 4 and so on, similar proof. And if x2 is, let me check this one, if x2 is minus 1, minus 1. Minus 2 is minus 3, again doesn't divide 2, and also for minus 3 and all of them, if you consider with y2, the difference doesn't divide 2. So again, we have no choice for x2, so d5 is also, for d5 equals 5, we don't have any answers. So the answer is, we said we only need to check for 1 to 5. 1 was good, we had a polynomial. For 2 also, for 3 we found, and for d equals 5 we didn't find, and also for d equals 4. So the only d that we found polynomial is when d equals 1, 2 and 3.